All right, welcome back to Introduction to Computer Networks. This is Polly again, and as usual, for the Wednesday sessions, we just have nothing special to announce, as many of them are already announced on Tuesday. And good morning. Okay, Felix. Yeah, it's okay. I sometimes mixes the time up. And Ying Xuan, Jia Dong, and Yu Qi, all of you, good morning. And today we're going to start from, guess what? Quiz 20. Let me go to the whiteboard mode. And let me make sure that quiz 20 there is on the Discord. Yeah, I see more of you popping in. Hey, just on time. Qianru Boyuan. Yeah, I probably stayed up too late last night. Okay, I'm not as spirited as I was as Polly today. Okay, but hey, let's go on. Such is life. This is quiz 20. Okay, so hey, we're gonna exercise RDT 3.0. We went through the whole RDT 3.0's finite state machine, particularly the sender side. We actually adapted from RDT 2.2, recall? All right, so you guys should have now some good sense of finite state machine and how it works. That's exercise. Okay, so this is the sender. And during the lecture yesterday, we did not cover receiver. Okay, here's the first time you see the receiver side of RDT 3.0. And you know what? Hey, it's the same as RDT 2.2. Isn't it? Yeah, that's why there's no slides particularly explaining RDT 3.0's receiver. Okay, so from 2.2 to 3.0, all that needs to be changed, just the sender side. All right, so the receiver is pretty much always straightforward, simple. Now let's try to see if we can interact. We can find the interaction between the sender and receiver and exactly which transition is triggered using a couple examples. So the first scenario is this. We send one packet and this packet is lost. Right? And then there's no more losses or bit errors afterwards. Okay, what will be the transitions triggered? Okay, between sender and receiver, and till the end, till the when both finite state machines will stop. Okay, when both systems stabilize. So this one is the simple scenario. There's a more complicated scenario. It's a little bit tricky for scenario 2. Again, we send one packet. Hey, the receiver receives the packet. Okay, but this time, okay, it returned an ACK, and that ACK carries sequence number 1. All right. But at the sender side, this ACK1 packet is received, but there's a bit error in this packet. Okay, wow, sounds complicated. All right. But there's no more losses or bit errors after this. So guys, think a little bit, okay? And take a look at the finite state machines closer. You guys have 3 minutes to work on these two scenarios given the familiarity of the finite state machines. So let's go to the score space. Okay, 3 minutes might be too long. All right, but 3 minutes. If we are done faster, we can come check on your answers faster. Okay, so let's start counting time. 3 minutes. I didn't notice that Ivan was actually asking a question. So we'll start from here, 0. Let me go back to the... Yeah, we always start from here, okay, if not specialized otherwise. Okay, so let's go back. Okay, good. I think Ivan, parenthesis, I will assume we start with these 0. And that is perfectly fine. In case there are situations that's confusing, feel free just, add some conditions in order for you to elaborate further. Oh, okay. Hey, as I was trying to say that, let's stretch the time a little bit, allowing you time to work. But I see Team 10, okay, submitting something. For scenario 1, T1, yeah, we send 1 packet, right? So let me clear this. We send 1 packet, and that would get lost. What would happen if it's lost? The receiver will never get the packet anyway. So yeah, it seems that we should be triggering this transition next, isn't it? So that should be T3. Yeah, Team 10, you're right on spot. Let's see. If a timeout occurred, oh, you know what? We retransmit the packet, isn't it? And there's no more loss or bit errors afterwards. Therefore, the packet would arrive at the receiver. So again, we start from here. Okay, and there's no bit error. So it should be taking this transition, isn't it? So T11 next. And then as T11 is triggered, we pass the data up to the higher layer, and we generate this egg, right, with sequence number 0, and this will go back to the sender. Sender, upon receiving the egg, will trigger, I think this is usually the one that everything is okay. So T4, because it's not corrupted and the sequence number is exactly 0, yeah, so we stop the timer and we'll rest here and wait for call 1 from above. Yeah, so for scenario 1, I see you guys are all doing great. Yeah, so Ivan, oh, thank you for helping everyone here, right? Very good. Team 12. Okay, Chengqie, yeah, you've mastered the finite state machine, right? So you send the next packet, and you did it all the way till you go back to the state 0, isn't it? To the wait for call 0 from above. Yeah, this is great. Yeah, it does look like for scenario 1, everyone finds it reasonable and solve scenario 1, no problem. Let's check out scenario 2. All right, so this one. Okay, yeah, I guess for some of you guys, for scenario 1, you thought that you would continue from where we rest. So I think Ivan, Team 10 here, will start the second packet, scenario 2, from here, which is also fine. Usually Polly actually gets what you were saying when I see your answer as well. So you assume that scenario 2 will actually follow the end states of scenario 1, which is fine. If you start again from the starting state, that is also fine. Yeah, Polly will try to be more clear, stating the condition for both scenarios if this is going to be in the exam. All right. So we send one packet and it comes through. If we are here, we send packet, then it will be the T6 transition, isn't it? And we'll rest here after the T6 transition. And we'll be sending packet 1 to the receiver. And receiver here will send return AC1. All right. So if sender here is at this state, receiver usually is also here. And in fact, at the end of scenario 1, receiver rest is here at this state. And so upon receiving AC1, upon receiving packet 1, right? So packet has sequence 1, therefore we trigger this transition, right? If it's corrupted or sequence 0, then we resend the duplicate, resend the old AG, which will result in a duplicate AG transition in the sender. But it's sequence 1, therefore we extract packet and send AC1. But this AC1 arriving here, okay, has a bit error. So sender is right here. Has a bit error that would actually trigger corrupt is AC0 here. And so does nothing, and then timeout will be triggered next. So yeah. Okay, so T6, T13, T7 triggered, and TA will be triggered next, isn't it? I see, Ivan. What's confusing for you? Because here, if we start the receiver side from this state, and as I said, this AC1 packet is received, but the AC1 packet has a bit error. The bit error is happening here. Okay, so your T7 is fine, right? But the sender will actually wait and wait. So the next event triggered is next transition trigger should be T8, isn't it, Ivan? Yeah. So it's not T14. Okay, think about it, Ivan. Yeah, scenario 2 is a little bit tricky, isn't it? Oh, I think what's wrong for Team 10, the return AC1 is received, but with a bit error. So it's the AC1 packet here having bit error. So you were right? Triggering T7. But right after that should be T8. Okay, and then T14, and then T9. So you just miss T8. All right, good. Let's see. T14. Yeah, I think similar. So T7 trigger, but TA needs to go next, right? To resend the packet. Therefore, triggering receiver to send the ACK T14, to trigger T14. Yeah, thank you, Chengji. I think after reading yours answer, I see what's going on. T1. Okay, so Chengji assumes starting from this state. T1 and T11. And then T4, interesting. So there's a packet. So T14 is triggered. All right, so that's interesting because, guys, so it's really tricky, this one, isn't it, for S2. If we start here, the answer will be different if we start here, okay? One packet is sent. So, that packet is sent. So T1 is triggered, a packet is sent, and we rest here at the sender side. That packet will arrive at the receiver, okay? But I did not say, right, anything about this packet arriving at the receiver, but I simply say, ACK1 is returned to the sender. So which transition, okay, will return ACK1? This transition return ACK0. This transition return a duplicate ACK, and the ACK previously generated should be this one, ACK1. So T14 is triggered correctly. So that is correct. Okay, so T4 is triggered next. T4 is this one here. Okay, so hey, Chengjie, should be T14 going back. Okay, think again. Okay, Chengjie. But what would be the sequence of transitions triggered now? So 14 will be triggered next. What is sent back is ACK1. Okay, so this will go back to the sender. It's received. So here we are waiting, right? It's received. But we have two transitions to choose. And you know what? It's received, all right, but with bit error. So which one, okay, is the transition trigger if there's a bit error in the receive packet? It's this one, right? It's corrupted. The ACK is corrupted. So we do nothing. Therefore, the next is, so T1 first, T14 second, and then T2. And then, hey, we also wait until timeout, T3, isn't it? And after timeout, we resend packet 0. And there are no more losses or bit errors afterwards. After arriving at the receiver is still at this state. Packet 0 is received. Therefore, we trigger T11 next instead of T14. And then the receiver would arrive at the wait for 1 from below state. And that packet will come back. And it's received without corruption. Therefore, we trigger T4 next. And then the sender side will come to the wait for call 1 from above state. Okay, and stop. So sender here will stop sending. Therefore, receiver will also just stop here. Okay. Are we getting it? Very good, guys. You guys are picking things up. Yeah. So if it starts from this state, this pair of states, the sequence is 1. But if you start from this pair of states, the sequence will be different. So I'm just seeing, I'll actually allow either way. So let me see if 正年 gets it right. T1, T11. Oh no, because it's sending back an AG1, right? So this one sends AG0. Haha, isn't it tricky? Yeah, so if you guys pick such that scenario to continue from wait for call 1 and wait for call 1, one is from above, the other is from below, then Q2 sensor is T6, T13, T7, T8, and T9. T8, T14, T9, yeah. Good. Chengjie finally gets it right. Caitlin gets it right. And all right. Very good. So anyone dare to try if we go back to wait for call 0 from above and wait for call 0 from below? Yeah, I guess you guys all follow the case. Let's see. Okay, Yo Cheng here. T1, T11. No. Yeah, it should be calling T14. Yeah. Fix 14. T2. T3. T11. T4. Perfect. Okay, perfect. All right. So we have simple solutions now, right? So for the first setting, okay, you have team 10 there to follow. For the second kind of setting, if scenario 1 starts again from wait for call 0, then it will be team 13's solution being correct. Okay, guys? Yeah, I would really appreciate, for example, Zhengnian, could you write the details out as well as what team 10 did? Okay, that will clear things for the whole class or for the students couldn't make it today. All right, great. I am just glad that we got these cleared. And the questions can be a bit tricky, isn't it? So I think part of the confusion comes from the way the question is asked. But you see that sometimes you need to have some communication first in order to make sure that you understand similar kind of communications in the future. All right, great. Okay, good. I see that you guys get the idea. And quiz 20 is so important. But you know what? We're done with quiz 20, and we'll move on to the series topic today. Yeah, RDT 3.0 finally working generally, right? In case there are bit errors, in case there are packet losses, it works. But it doesn't work all that great, especially when it comes to link utilization. Okay, so this video next 6 minutes, Polly would calculate the utilization of a link of a connection between the sender and receiver. Okay, using RDT 3.0 and point out how low the utilization is. RDT 3.0. We spent quite a lot of time talking about it, and finally it seems to be working for the bit error case and the packet loss case. And you know what? It works indeed, okay, but it does not work that well. Okay, let me use this example here to explain. So let's suppose we have a pair of sender and receiver. In between them, there is this link, 1 gigabits per second. And the propagation delay one way is 15 milliseconds. And between the sender and receiver, the packet size is 8,000 bits. And that is the equivalent of 1 kilobyte. So this is very typical of a TCP connection's packet size. And you see also earlier doing the trace routes, 15 milliseconds is very typical between two routers on a local area network. And 1 gigabits per second link, this is very commonly seen. Some of the Ethernet connections are actually 10 gigabits per second already. Now, let's try to calculate. First, the transmission time. Well, you learned already in chapter 2, right? It's the packet size divided by the transmission rate. So packet size, transmission rate, 1 gigabits per second. And we get 8 microseconds as the transmission time. Now, the performance we'll be looking at here is this, the utilization of the link between the sender and receiver. Okay. If this is high, that means, ooh, sender is actively sending all the time. So usually the throughput is going to be better. Okay. But if the utilization is low, the throughput is not going to get any better. All right. Now, in order to calculate the utilization, let's recall how RDT 3.0 works. We send from the sender one data packet, and the sender there stop and wait for data to travel to the receiver. Receiver sends back an ACK, and ACK travel the network again back to the sender. And that's when the sender can decide whether to send another data. So sender there again, stop and wait until data travel to the network, ACK travel to the network, and then send another one. So you see that the sender there is working in cycles. Stop and wait, stop and wait, stop and wait. And each cycle, it's using this much amount of time to transmit actual bits, and this amount of time, so plus the round trip wait entirely for the entire cycle. So this is 0.008 millisecond, and this part, sending the packet and then wait, one wait and another wait. And here I'm ignoring the add packet transmission time, because add packet is usually just very small. Okay, so that's one round trip time plus packet transmission time, 30.008 millisecond. So overall utilization on this link is very, very low, 0.00027, too many zeros. And if I illustrate the scenario I just described there, sender, receiver, and this is timeline. Okay, at time 0, first packet bit is transmitted. So right here, first bit goes onto the link, and it takes this amount of time. That is the time to transmit all bits on the packet. So last packet bit transmitted is right at this time. Okay, that is the packet transmission time, L divided by R. And these bits, it's going to travel halfway to the receiver and another halfway back to the sender. So first packet bit arrives right here. This is what? The propagation delay. Okay? And this is also propagation delay. So 2 propagation delay plus L divided by R. This is one cycle. Within a cycle, only this amount of time sender is being active. Okay? Only this amount of data is being transmitted. While the entire duration, right? The sender can just keep pushing bits out, okay, onto the network interface. So you see again, the network utilization, L divided by R over the entire term, RTT plus L divided by R. Very low utilization. And that low utilization can be translated here. The throughput on the 1 gigabit link is only 270 kilobits per second. This is not even enough to send any video that would be sensible. So you see here, RDT 3.0, the design itself, although it works, but it limits the use of the physical resources. Okay, we're only sending one packet and then stop and wait until we can send another one. Now that I show this plot, then you know, obviously to increase the utilization is to send multiple packets per round. Indeed. So let's look at the plot in a bit more detail, just like we did in the previous slide. So sender, receiver, and timeline again. So this is the time we send the first packet, the end of the first packet. This is the time, first bit arriving at the receiver, last bit arriving at the receiver. At this point, the receiver can send back acknowledgement. So this is the time the acknowledgement arrives at the sender. This is the sender can begin sending the next round of packets. So how long is a round this time? Well, this is one-way delay, right? This is also one-way delay. So round-trip delay plus L divided by R. So the same. In each cycle, we now send multiple copies of packets. So now we're sending 3, so 3L divided by R, right? So utilization is now 3 times higher than the stop and wait scenario. All right, so you see, within one round trip time, if we just send one packet, that's low utilization. And pipelined, okay, RDT is the solution. And we've heard about pipeline term, this term, the second time. Recall in HTTP, right? So one type of the connection mode is what? Pipelined, isn't it? Persistent connection with pipelining. So it's the same technique. So to speed things up, to make sure that the response time is shorter, or to make sure that the file transfer time is shorter. Yeah, we do this thing very often, pipelining. So this next video, let's move on to talk about pipelined RDT. Okay, so there are actually 2 flavors. So in this introductory video, you will see how we will be sending multiple packets in one round trip at a time, and an overview and comparison of the 2 types of pipeline RDT. And this takes us to this new class of RDTs called the pipelined protocols. Okay, what it said is, let me repeat myself, the sender allows multiple packets being sent per round, okay, or multiple packets in flight. By in flight, I meant that these are just data packets going out. They are not yet acknowledged. So it's illustrated better here. So this one on the left is stop and wait. This one on the right is the pipelined RDT. So we see multiple data packets go, not yet acknowledged, and their acknowledgements will come back in a sequence, okay, in a round to the sender. Okay, so a range of sequence number needs to be increased. So previously in RDT 3.0, we used just 1 bit, right, 0 and 1. But now we need to allow multiple packets going out simultaneously. And we need to make sure that we acknowledge each of these packets. So we need to tell each of these packets in flight apart. Well, the sequence number definitely needs to be expanded. And we'll need buffering at the sender and the receiver side as well. Because, hey, what if multiple of these packets in flight are dropped? They need to be retransmitted again. So buffer definitely at the sender side is required to store those packets that are not yet acknowledged. Receiver here will also need buffer space because when this packet is lost and there's other packet coming in subsequently, should we keep them or should we drop them and have the sender retransmit again? And what about these other packets that has already arrived? Okay, so there's some buffer space also, okay, needed in order to address different needs of different designs. So buffering required, a longer range of sequence numbers required. Okay. Now, in the next few slides, what we're going to introduce are just 2 different flavors of these pipeline protocols. So they are the big categories. First is the go back end. The second is selective repeat. Now, one can, of course, further tune the go back end so that it works slightly differently. Hopefully, the second version works slightly better than the fundamental version. Similarly for the selective repeat protocols. Okay, so here's the overview slide that contrasts the 2 big categories of pipeline protocols. On the left, the go back end. On the right, selective repeat. Right? They are the same this way. Okay. Both of them allow having multiple packets in flight in a round. Okay. Well, that's the basic ideas of pipeline protocols. They must be the same this way. And then everything else will be different. First of all, okay, what the sequence number in the ACK packet means, very different. One is to indicate I'm acknowledging an individual packet. So when the receiver in selective repeat sends an acknowledgement, that sequence number in the acknowledgement is to acknowledge exactly the data packet carrying that sequence number. But for go back end, the receiver sends back acknowledgements, but the acknowledgement carries a sequence number such that all the data packets before that sequence numbers are acknowledged. So this is a bit odd. Okay, so that one sequence number seems to be acknowledged all the packets before that.
But the fact is that what the receiver is doing is this. The receiver will not add packets if it arrives and the receiver finds that there's a gap in between. So packet 1, 2, 3 missing, 4. Okay. When 4 arrives, the receiver does not send back acknowledgement 4. Instead, it sends acknowledgement 2 because there's a gap in the middle. So what the receiver of go back N here is saying is, I'm actually telling you to which point I do have consecutive receive data packets. Okay. So the next one is, the beginning of a gap, definitely. And the two categories work also very differently here. Timer. Okay, if you recall in RDT 3.0, we need a timer in order to tell whether a packet is dropped or not. Yes, go back in and selective repeat. Both of them implements timer. Okay, but in selective repeat, there's one timer for each packet that is still in flight, not yet acknowledged. Okay, so one timer, one packet. But for go back in, there's only one timer for the oldest unacked packet. So in one round, there'll be a lot of packets being sent, multiple packets being transmitted. Okay, there's going to be just one timer for the oldest unacked, meaning if you send one flight out, there's just going to be one timer for the first one in that flight. Okay, and if the first one is acknowledged, there'll be a timer for the second packet that is now the new oldest packet that's not yet active. Okay, so one timer for a flight of packet in go back in. And the last difference is this. Okay. For selective repeat, when timer expires, the sender only retransmit the unacked packet. So whatever that timer says, if this is for sequence number 10, then it only retransmits packet 10. But in go back in, when the timer expires, it's going to retransmit from that oldest unacked packet. So all the unacked packets from the oldest one to the newest one. All right. So each timer is going to trigger retransmission of the rest of the flight of the packets.
All right. So one, go back in. So the unit of tracking is a flight of packet. The second one, selective repeat. The unit of tracking is individual packet. Okay, multiple packets, individual packet. Good. Now, next, let's get into the detail of the first pipeline RDT, go back in. All right, so Polly is going to introduce go back in 3 videos. The first video is to introduce the data structure. So that flight of packets, go back in sender, will be tracking, is managed within a window. And to maintain the window in terms of coding, we use 3 variables. So this video give you an overview of go back in and how these packets are tracked in a window.
Now let's look closer into the first categories of the pipeline RDT, the go back in. So this is just the sender side, and we'll come to the receiver side in a couple slides. And first thing first, the packet sequence number in go back in. If you recall in RDT 3.0, we only allow one data packet goes in out without being acknowledged, isn't it? And in that case, we just need 1 bit sequence number to tell the old packet and the new packets apart. But now go back in being a pipeline RDT, which we allow multiple packets being out in transit without being acknowledged. So your intuition should also tell you that, hey, you need a higher number of sequence numbers to tell all these in-flight packets apart. You are correct, and we now definitely need more, and k here is obviously larger than 1. Okay. Now, having k bits in the packet header, okay, as the sequence number field, then you see the sequence number can range from 0 all the way to 2 to the power of k subtracting 1. And next, in go back in, or generally the pipeline RDT, we do have this thing called the sending window. And the sending window is usually associated with the limit, okay, we call the n, or the sending window size. Okay, so n here is to limit the number of unacked packets allowed. Right? And go back in, this is the number of consecutive unact packets allowed. It's also illustrated here. Okay. From the first packet in flight to the last packet in flight, the max range is n. Right? So at any given point in time, we allow only up to n packets being in transit, not yet acknowledged. And so you see here, this thing is also called the sending window, right? And n here is the sending window size. Now let's take a closer look at the plot over here. So each of these slim rectangles are packets. So the green packets are the very early packets that are already sent and already acknowledged. So this is in the middle of the sender transmission, as you see. Okay. And yellow packet, starting from here, the send base. So this is the first packet that is being sent out and not yet acknowledged. And there will be a number of these. So yellow ones are the packets already generated and sent, but not yet acknowledged. Okay. Now, depending on the application level source, the message could be large or small. Okay, so this is illustrating a case when the message is not that large, meaning you don't need to generate that many segments at the transport layer to cover the entire message. So potentially, within the limit n, we might have some sequence numbers that allow us to generate packets to send out, but we don't really need them. So the blue ones are usable, but not yet sent. Okay, so essentially, yellow plus the blue ones should be less than n. Right? Now, to indicate the beginning of the usable packet sequence number, we use yet another variable, the next seek number. Right? So send base, or sometimes I just call it the base, okay, is the base of the sending window. Next seek number is the next available sequence number that we can generate data packet within the window n. Right? And the last one, so these blank ones are simply outside of the window limit, so not usable. Right?
All right. Okay. So that was the window, right? We see three variables: the send base, the next seek num, and the window size n. So the three variables define, and track the packets can potentially be in flight. And there was a question from Ivan saying, what does usable packets mean, right? I guess you were asking about the blue slots. Those are the slots, okay, according to the window size, okay, that the sender can send. But sometimes the sender may not have more data to send. So then you get to see some blue slots. If the sender is very busy, lots of data to send from the application layer, then I'm pretty sure that all the slots in the window are yellow, occupied. Okay, so the blue slots are sometimes when the sender is actually not that busy. Then the sender side window is not fully utilized. Okay, I hope this is clear. And now let's move on to the next video. You see that the window will slide as acknowledgement packets come back. All right, great, Ivan. Thank you for the feedback. Now let's check out how the window slides.
And here, let's assume, okay, send base here finally receive an acknowledgement, and it's acknowledged, so we turn this into green. What do we do here? Now this one is green, isn't it? So send base is only to indicate the first unact packet, so we actually need to change it to this packet sequence number. Right? As a result, we shift the window, and it's beginning from here, and include the next blank packet and turn it what? Blue. So the window is actually sliding over by one packet. Okay, so such a window is also called the sliding window mechanism. So when acknowledgement packet is received, you see these yellow packets turning green gradually, okay, and the window sizes is sliding over and then casting more blank packets into blue ones. All right. Just to make sure that it's clear, send base is the variable in go back and sender that always points to the base of the sending window, which means it's always the first yellow packet's sequence number. So the send base will only be changed when the first yellow packet is acknowledged and turned into green. So send base can no longer be pointing to a green packet. And as a result, it needs to be moved to the sequence number of the first yellow packet now. Right? And you see window then here is sliding over by 1. The next seq num is always pointing to the next sequence number in case we need to generate a new data packet. So in this scenario, it's pointing, of course, to the first blue packet that is useful and not yet sent. So because when we get a call from above and if we need to generate a data packet, then we'll turn this blue one into yellow. And the next seq num is going to be shifted over and reassigned to the first blue packet after sending. And we do not shift the window size at all because the send base is not changed and the n here is a constant. But be careful though. There will be scenarios where, hey, all these blue ones are actually yellow, meaning, the sender does have large message to send and we are actually exhausting the entire window size to send the message already. In that case, the next seq num will be pointing here at a blank packet. Okay, that is the next available sequence number to generate a data packet. But it's not quite yet pointing at the blue one because, there's no blue packet at all. All right, so next seq num, to be very precise, it's just to point into the first sequence number in case we need to generate another data packet.
All right, so you see that the 3 variables might change as X are received and having more data to send. Okay, good. Last video is just to repeat what Polly has already said in the overview. We use a timer to track in case there's packet loss, right? So this one is brief, almost 22 minutes.
The rest of the go backend you heard a little bit already about. The ACK, the sender received, is going to be a cumulative ACK. Okay? What it means is that in the sequence number of the cumulative ACK, it indicates all the data packets before this number n are acknowledged. Okay, so all packets before n, including n, are green. All right. Now, if the sender receives duplicate acknowledgements, so hey, ACK n has already been received, but the next moment another ACK n is received. What does that say? If you recall earlier, that usually meant, packet n plus 1, there is a gap at the receiver. And receiver does not send acknowledgement up to sequence number n if there is actually any gap before it. Right? So receiving of a duplicate ACK at sender side indicates, whatever n is plus 1 is a packet that's missing. Timer. There is only one timer for an entire flight of an ACK packet. So it's a timer associated with the base of the in-flight ACK packet train. Okay, so that is essentially this. The oldest in-flight ACK packet is always indicated by the send base. In a way, there's a timer associated with the send base, essentially. Whenever the send base is changed or whenever the send base is refreshed, we refresh the timer or restart the timer. If it's been unfortunate that we do have packet loss such that the timer needs to time out, then we retransmit the entire flight of packet, starting from n all the way to the highest number that's not yet ACK. So that means starting from the send base all the way to the last of the yellow packet. So timeout indicates the entire flight of the yellow packets will be retransmitted.
All right. Now it takes us to quiz 21. So that's exercise, right? Sliding windows. Let's go to the PowerPoint mode. Okay, so Polly is asking, given, the sender window looking like this right now. The send base is 23 currently. The next seq num is 33. And the first gray packet, which is essentially send base plus n, is 39. All right. Q1 asks, what will be the values of the 3 variables? Sending 4 more packets. So hey, Ivan, you will see that these blue packets will be useful. Okay, so what do? Yeah, we need to turn those into yellow, isn't it? But that is done by changing the values of these three variables. Okay, and not all the variables might be changed depending on the action you need to react to. Okay, so guys, play the role of the go back and sender, thinking, hey, what should be the send base value, next seek number value, and first grade packet value when you get 4 more packets from above? Q2. Okay, and this is not one after another. So each of the quiz will start from this scenario, okay, from this setting. Okay, so given these 3 original values for the 3 variables, hey, if we receive an ACK for packet 28, ooh, okay, would the values be changed? And Q3, if we receive an ACK for 32, so given the setting, receive ACK for 32, will any of the values need to be changed? Okay, so this is quiz 21. Guys, go on to the Discord space. I see. All right. Okay. Hey, no worries, guys. Yeah, some of the classmates, they are, mythically excellent predicting what Polly will do next. Okay, so no worries about that. We're gonna be taking a break anyway. It's 11:11. Let's take a break, and during the break, guys, work on quiz 21, and we'll come back to check on your solutions 11:21. Okay, so break and quiz work time. Hi guys, yeah, it's time to come back. And having the general mechanism of go back and introduce, by the way, uh, those who are keen and pay attention to the video earlier, all that we talk about go back in is just the sender side. You know what? The receiver side is as straightforward as RDT 3.0s. Okay, but does still somewhat, excuse me, but still somewhat different, as the AG will be accumulative. Okay, so but let's check out the finite state machines of go back in. All right, so to introduce the sender of go back in, Polly will use 3 videos. The first video is actually brief, a quick review of RDT 3.0 sender.
Go back and sender's finite state machine. Before we start talking about this, let me review RDT 3.0 sender's finite state machine. And here it is, the RDT 3.0 sender. Okay, so we're starting here. Okay, and there are 4 typical transitions: 1, 2, 3, and 4. So first is to get a call from above. We generate the packet starting from packet 0, send it out, and then start the timer. The other is getting a feedback from the receiver. If it's not corrupted and it is indeed the ACK we're expecting, then that's a positive acknowledgement, so we stop timer and move on to send the next packet. Third is when it's a little bit unfortunate, the packet is not correct or not arriving at the receiver, timeout will be triggered. So we retransmit the packet and start the timer again. Last one is when you get the feedback, it's unfortunately corrupted, then we do nothing. So we kind of ignore these 2 conditions on purpose. The second condition is, yeah, we get an ACK all right, but this is what carrying 1, which indicates this is a negative acknowledgement. So in these 2 cases, instead of quickly retransmit, we just ignore. Right, so this is a quick refresh of RDT 3.0.
All right, now next, the sender side of go back in, and we'll introduce the 2 transitions that are triggered more often.
In go back in sender finite state machine, we also have these 4 transitions: getting a call from above, receiving feedback from the receiver and it's not corrupted, having the timeout event, as well as getting feedback from the receiver but it's corrupted. Okay, very similar. And then we go through them one by one. Now let's start from the getting a call from above transition here. Comparing to RDT 3.0's getting call from above transition, this one is pretty long. Yeah. And it starts from a if-else condition check. And the condition is this guy here. If the next seek num is less than base plus n, so base plus n is what? The window range, isn't it? If the next seek num is within the range, that means, okay, we can now generate still some data packets. So, makes sense. We go ahead and create the packet using the data from the application layer, generate the checksum for the data, and then give it the sequence number. Okay. Here. We are now using an array of send packet here to store all the packets being generated. This is because go backend is a pipelined RDT, meaning there will be multiple packets in flight, so they'll be generated, being transmitted, but not yet acknowledged. So these send packet will need to be stored temporarily at the sender before they are acknowledged, because chances high that you need to retransmit it somewhere later. Okay, so we need an array instead of just one packet there to store the packets that are in flight. Next step, send the packet out. Oh, and then we need to start the timer, right? This is to handle the cases we could have packet losses. Just like in RDT 3.0, the difference to RDT 2. something is to have these timers. So we need to start timer, definitely. But in go back in, we have one timer for the entire flight of ACK packets. So we need to check, right? We cannot be starting a timer for every data sent. So here we're checking. If the packet we are now generating is indeed the base, the first yellow packet, because the timer in go back in is associated with the first yellow packet, so associated with the base. So only when the packet we are generating is the base, then start timer. Otherwise, don't. So this ensures that we have only one timer for one flight of an ACK packets. And the last is straightforward, just increment the sequence number by 1. Right? So this is if the next seek num is within the window. Otherwise, yeah, refuse data. So this is telling the application layer process saying that, hey, I cannot be sending more data packets. So you hold on and you try calling the RDT send after some time. And the second one that we'll examine is this guy here. All right, so this is supposed to be the case where we receive acknowledgement, and it's a new one, therefore we could move on. All right, so let's take a closer look at how the move on is like in go back and sender. First of all, the checking condition. Yeah, get a feedback packet coming from the receiver from the lower layer. And if it's not corrupted, oh, good. So the feedback packet is not corrupted. So this must be one of those cumulative ACKs. So inside the ACK, there's going to be carrying a sequence number. So why don't we get that sequence number out? So get ACK num. Okay, so this is a new function call introduced into go back and finite state machine. So that is just a bit abstract, but what it does is to get the sequence number in the cumulative ACK packet here. All right. And we simply change the base to that sequence number plus 1. All right. So this is the first packet that is unacked. Hey, makes sense, right? Receiver sends a cumulative ACK. So that ACK carries the sequence number n, which indicates all the sequence numbers before that, including n, are acknowledged. And the n plus 1 is the first in the gap at the receiver. The first one, that ACK cannot be acting. Okay, therefore, base is assigned to that value. Okay, makes sense. Oh, but we check. So just like in the generating data part, there are a lot more check. Being careful here. If the base is nulled, the next seek num. What does that mean? Base should be the first yellow, and next seek num should be the next data that is allowed to send. But next seek num cannot be a yellow packet, right? So if they are the same, that means there are no yellow packet at all in the window. Okay, which means all the packets that's not yet ACKed at this point in time are already ACKed. Okay, so stop timer because there's no pending packet waiting for acknowledgement. Otherwise, yeah, restart timer. So we receive a cumulative ACK. The base is reassigned such that it's pointing to the first yellow packet. Okay? And so we refresh the timer for the first yellow packet for the base. Okay? So restart timer. Right? So the only thing that's a bit odd is this. There's an if condition to check whether we should stop the timer because all standing packets are cleared. All yellow ones certainly turn green. Or we need to refresh because the base is either refreshed or changed to a new value. And therefore, we need to restart the timer for the refreshed first yellow packet.
Yeah, so this is our go back and sender. It's very unusual, right? Previously, in the sender side of the finite state machine, we see at least 2 states, right? Call from above for data, and then wait for ACK from below. And there'll be transition going this way, and then another transition going to the wait for call from above. Okay, but another sequence number. And then there are 2 transitions. One is handling corrupted ACK. The other is waiting for timeout, things like that, right? But if you think about it, yeah, there are just, simply 4 transitions possible. Okay, so in go back in, we kind of merge everything into one state. And this state is just waiting for call from above, waiting for ACK from below. And then, hey, the next video is, of course, handling the corrupted packet or packets with ACK packet with duplicate ACKs. And then the other one, timeout, and then retransmit. Okay, so that's the next video.
And the third transition is straightforward. It's actually very similar to RDT 3.0's timeout event. Yeah, we restart the timer and retransmit the packets. In RDT 3.0 sender, we retransmit only 1 packet, but this time in go back in, we retransmit for the entire flight of packets starting from the base. to the packet right before next seek none. And the fourth transition is this: when the sender received a feedback and it's a corrupted feedback, then we do nothing. So this is just like in RDT 3.0, when the sender receives a corrupted ACK or a duplicate ACK, which is a negative ACK, it does nothing. Okay. Now the difference here though is that it only handles the corrupted ACK case. What happened to the duplicate ACK? In go back and sender, yeah, it's actually handled here. When the sender receives an ACK, it's duplicate ACK, the actions are the same. If it's a new ACK, the base, yeah, will shift, yeah, to the right. But if it's a duplicate ACK, if it's a duplicate cumulative ACK, the base will remain the same. Right? Would this be a problem? Now, some of you might not be very comfortable with this, right? Because, hey, if the base remains the same, what do we do here? Yeah, we'll be definitely in this situation, right? Yeah, there's an unact packet somewhere and the base remains the same. We'll be restarting the timer, meaning the first time that base is receiving an ACK for all the packets before the base, the timer for that base has already been started. And now we're reassigning the base to the same value and restart the timer. That means we're extending the timer interval, yeah, for that base. How do you like that? Think about it. And the last bit of the go back and sender, or shall I say the first bit of the go back and sender that we actually talked last, is the initialization of the sender. Okay, so the base, starting of the window, is initialized to sequence number 1. Next seek num is also initialized to sequence number 1. So this is unlike the RDT 3.0 sender receiver, always starting from packet sequence number 0. In go back and sender, textbook authors decide suddenly that they want to start from the sequence number 1.
Okay, so yeah, so the other two transitions are relatively more straightforward. But you can also see that given a mechanism, the description is there, but you can actually come up with different kinds of finite state machines to describe the mechanism. All right, so go back and sender being very different from RDT 3.0 or even further earlier RDT or different is an example. Good. Now let's check out the receiver finite state machine. This one is relatively easier than the sender side.
Now, the receiver finite state machine of go back in. It's actually quite simple. Let's just skip the initialization and focus on the two transitions possible. Among the two, this one is the more straightforward. We receive a data, get a call from below, and check the data, it's not corrupted, and check the sequence number of the data. Has seek num there is a function newly defined for go back in again. So what it does is simply, okay, checking the sequence number in the data and see if it matches the expected sequence number, which starts from sequence number 1. So if we receive packet 1 and it's expected, extract data out of packet 1, pass the data up to the application layer, generate ACK packet for packet sequence number 1, send the ACK out, increment the expected sequence number. Okay, so this is the simple case where everything works as expected. No error, no loss. And the second case is the default transition. What default meant is just all the other conditions that's not matching the previous transitions condition, which means the data can be corrupted or the data received not corrupted but not carrying the sequence number expected. So here, corrupted data or data packet that's not in the expected sequence number. Now this could be a duplicate data packet. This could also be a data packet carrying the future sequence number. So in either case, which means default is just to send the same packet again. That is the packet generated here, which is the ACK packet that is generated previously when data arriving correctly and in sequence. So in case of corrupted data, out of order data, we discard the data, no receiver buffering, so there's no extract of data, no passing of the data up to the application layer. And all we do is simply react, okay, to the data with the highest sequence number arriving correctly in order. So go back and receiver there. Works a bit odd, not that intuitive, but it's very simple. Okay. It always acknowledges to the data packet that is the highest in sequence number for all those who arrive correctly and in order. So all the receiver needs to track is the expected sequence number. And that's pretty much all. At the sender side, if a duplicate ACK is received, that is essentially saying either the data previously sent is corrupted or the data previously sent is lost.
Yeah, so receiver of go back in can sometimes receive packets that's out of sequence. But these packets, although arriving fine, they will be discarded. Do you like that? Okay, so Polly actually added a pop-up quiz today asking, do you like go back in receiver doesn't do receiver buffering? And while you are thinking, so I'm asking a simple question, like or dislike, okay? If you have a reason, definitely add to that. Otherwise, let's come back to go back in. And this time, let's walk through an example. So go back in, being needing to handle multiple packets in a fly is substantially more complex, okay, when you see the packet interaction. So this example is going to take us 12 minutes, and Polly is going to break it into two parts. First part, you will see how the packets are sent back to back from the sender to the receiver. And you will see also how the receiver react to these packets arriving or not arriving. So this first video about 6 minutes.
Next is to walk through an example of go back in, following the finite state machines. So then we go back and recap, go back and sender's finite state machine and the receiver finite state machine, just so that you can follow. And real quick, the sender side of go back in is this. If we get a call from above, we check real quick whether next sequence number is within the sending window, which is base plus n. If it is, okay, then we generate packet and send it out. And then check whether we should be starting a timer. And the condition to start the timer is if this next seq number is indeed, okay, the base, and then increment the sequence number. All right, so check whether the next seq number is within the sending window. If so, generate the packet, send it out. Check whether we should start the timer. So next seq number, whether it equals the base, and then increment the next sequence number. If we do not pass the condition whether the next seq number is within the sending window, then ask the application layer process to wait. All right. Now, back to the example. Let's assume the window size is 4, okay, and the sender's application layer process is sending data all the time. So sender here gets call from above all the time. So let's see. In the first call from above, all right, the base and the next seq number are both initialized to 0. Now the first call from above is going to trigger, checking whether the next seq number is within the sending window. Sending window starting from base and window size is 4. Next seq is initialized to 0. Is 0 less than 0 plus 4? Yes. So we generate the packet, send it out. And next to what? Check whether we need to start the timer. And the condition to start the timer is only when the next seq number equals the base. Next seq number is 0. Base is 0. Cool. Okay. Packet 0 is indeed the first of the first flight. So start the timer here. All right. And next is just to increment the next seq number to what? 1. So next sequence number here at the beginning is 0. Now increment it to 1. So if we get a call from above again, next seq number, is it less than base, still 0, plus 4? Yes. So generate packet 1. 1 here is the next seq number, isn't it? Send it out. Check whether we should start the timer. Next seq num is 1. Base is 0, not matching. So the second packet in flight does not start timer. All right, just increment the next seq num. So here, The third call from above will start from next seek num equal to base 0 and 4. Is 2 less than 0 plus 4? Yes. So we generate yet another packet. Next seek num equal to, send it out. Do we start a timer? Next seek num equal to base 0, therefore not matching, not starting timer. Increment the sequence number to 3. Right? Is 3 less than 0 plus 4? Yes. Generate packet 3, send it out, not start the timer because next seek number is 3 and base is still 0. Right? And we increment the sequence number to 4. And now we get the fifth call from above. And that call from above will check, is 4 less than base 0 plus 4? It's no longer less, right? So what do? We go to the refuse data part of the if condition. So yeah, the application layer process is asked to wait, and sender will pause sending for now. And these packets will go out to the internet and hopefully reaching the receiver, while there's a timer that's ticking and ticking, ticking, and that is associated with the base, the packet 0. All right. And here's to quickly review the receiver go back in. If we get a call from below, the data is not corrupted and carrying the expected sequence number, simply extract data, pass to the application layer, generate the ACK, send the ACK, and increment the expected sequence number. And otherwise, just resend the ACK that has been generated previously. Now, the receiver. Okay, receiver here will be receiving packet 0. Yeah, it's not corrupted and it's expected, right? So expecting sequence number 0, receiving sequence number 0, therefore we send ACK, expected number 0. Next, yeah, we get a call again from below, packet 1, not corrupted, and it's in sequence, therefore we send ACK for the highest data number that has correctly arrived and arriving in order. So these are being sent back to the sender. But packet 2, oops, is lost somewhere on the internet. But packet 3 will arrive. It's not corrupted, but is it expected? We're actually expecting what? Sequence number 2. So we do not extract data. We actually trigger the default transition, if you recall, and just resend the ACK that is previously generated. So ACK 1 is being sent again. So right here. All right.
All right, so that was the first part of the example. The second part is that you see at the sender side, how the sender reacts to the X coming or not having X coming.
And now we come back to the sender side. Okay, we'll be receiving ACK 0 here. All right, so receiving ACK 0. It triggers sender finite state machines. Oh, the transition at the bottom, isn't it? Receiving a call from below. Yeah, receiving a feedback packet from below. What do we do there? Yeah, let's recall and go back. Yeah, so here, quickly recall. Okay, this transition, getting a packet from the lower layer and it's not corrupted, what do? Set the base to the sequence number in the ACK packet plus 1. And then we check whether we need to stop timer or refresh the timer. Now, only when the base and the next seek num are equal, then we stop timer, because the base here is empty, meaning no yellow packets at all, because next seek number is the first blue. So only when the base and the next seek number are the same. Otherwise, restart timer. Okay. Now we can come back here to examine. Yeah, what is the action the sender should be taking? Okay. First, receiving ACK 0. So that's triggering the transition at the bottom, a feedback coming from the lower layer, and it's not corrupted. So what we do is to extract the sequence number in the ACK, add it by 1, and that will be the new base. So base here is moved by 1 position. The next thing we do is to check whether the base equals the next seek num, right? If they are the same, that means we should stop the timer, because hey, all the data packets are already added, right? But otherwise, then we restart the timer. So hey, base is 1, next seek num was previously 4, isn't it? That's why we are waiting here. Okay, so Oh, we cannot be stopping the timer. Instead, we should what? Restart the timer. So this timer here, original ticking, will be canceled and we restart the timer here. And that timer is going to be associated with the new base, which is 1 over here. All right. And then, hey, sender is trying to send data. So quickly get a call from above. So we trigger the top transition. Right? So next seek num is 4. And 4, is it less than the base 1 plus the window size 4? So together 5. 4 less than 5. Cool. We can generate packet 4 and send it out. Is the sequence number base equaling the next seek num? No, so we do not start timer here. All right, so base is 1, so that means base, there's already a timer running. All right, next seek num, 4, not equaling 1, so not starting a timer here for generating packet 4. So timer is still associated with the base 1. All right, and then we increment the sequence number by 1, so 5 here. Okay. Similarly, receiving ACK1, oh, we set the base to 1 plus 1. So the base is now what? 2. Is the base identical with the next seek num, which is 5? No. Therefore, we do not stop timer. But instead, we restart timer. So T removed there. And T is restarted with the new base. That is 2 over here. Okay, so T for 2. So this is T for 1. And this is T for 0. And at this point, one slot open up, getting call from above. Yeah, 5 is less than 2 plus 4, 6. Therefore, we generate packet 5 and send it out. And do we start the timer? No, right? And increment the sequence number to 6. And yeah, another ACK1 is coming in. Okay, this is triggered by receiving packet 3 without packet 2. So ACK1 comes in, triggering the bottom transition, not corrupted, set the base to 1 plus 1, 2. Well, that is the same. All right. Base and next seek number, still not matching. Therefore, we restart timer. Ooh, so, hey, we actually killed the old timer for base 2. Now, restart timer for base 2. That means, wow, this base is actually, waiting a longer time to expire to retransmit. But it's okay. It will still work. Just wait a bit longer. Right. If we get a call from above now, all right, next seek is 6, and base is 2. 2 plus 4, also 6. 6 not greater than 6. Therefore, we again wait here. All right. So, yep, pretty much wait here. And so this timer for the base 2 is going to tick, 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 tick. All right. Let's assume packet 4 and 5 arrive at the receiver side, which generates react of packet 1 because they are out of order. And let's just assume these two acts is just going to take a long time to come back before T for 2, the second time here, times out. Okay. What's going to happen here is that it's going to trigger the sender side, the timeout event. What do we do there? We restart timer and what? Retransmit the entire flight of packets starting from the base. So 2, 3, 4, 5 go out at once. All right. And good thing is that at the other end, the receiver here finally gets packet 2. Yeah, it's finally the expected sequence number, so it's going to call the transition on the right, extract data, pass it up, so deliver to the application layer, and therefore we generate ACK2. And packet 3 arriving here, extract data, and then generate ACK3, and so on and so forth.
All right, so that's a full example. Okay, hope you guys are following fine, because Polly personally have trouble following the example the first time. Okay, but after recording the videos, I get a better idea how go back and works. And now we switch gear to selective repeat. Okay, so this is the other kind that actually does ACK per packet, that does timer per packet. Okay, to be honest, Polly felt that the selective repeat is much simpler than go back in to track. Okay, so here's the introduction, which is about 5 minutes.
Selective repeat. This is the second big categories of the pipeline RDT. So its design is pretty much the opposite of go back in. So in go back in, you have cumulative act. So the sequence number in the act there is to indicate all the packets before this particular numbers are received correctly. But in selective repeat, the acknowledgements are individual. So one acknowledgement packet per data packet. The sequence number in the acknowledgement is only to acknowledge one data packet. In go back in, we have one timer for an entire flight of packets. When that timer times out, we retransmit the whole flight of packets. In selective repeat, the opposite. We have one timer per data packet. When that timer times out, we retransmit just that data packet. All right, so receiver will acknowledge each correctly received data packet individually. Sender will only retransmit a packet when the timer for that packet expires. Very straightforward. The slight tricky part of the selective repeat is at the receiver. Okay, we now have to buffer packets arriving out of order. And the reason for this is very straightforward, very simple. If we send packet 1, 2, 3, and 1 arrive at the receiver, 2 get lost, 3 arrive at the receiver. You cannot be just extracting the data bits out of packet 1, pass it out to the upper layer, and not passing the bits of packet 2, and immediately pass the data bits in packet 3, and then later pass the data bits in packet 2, because that way you get bit sequences that is out of order at the application layer. And our definition of RDT is that all the bits arrive reliably and in order. So receiver here in selective repeat, the implementation gets complicated. You need memory space to store temporarily the packets arriving out of order. You wait until all the gaps are filled, and then you pass all the data bits up to the application layer in sequence. The only thing that remains the same is there is still this sending window, which is limited by n, from the base to base plus n. Now, be a bit careful in selective repeat though. What we are limiting there is the sequence number of the unact packet. So what is the maximum sequence number there can be unact. As opposed to in go back n, we say n being the number of unact packets. The reason that I'm saying you need to be careful is because of this. From the base to n plus base. Yeah, there are yellow packets, all right, and after the yellow packets, the blue packets. In go back n, they're just gonna be yellow and blue. So the number of yellow packets maximum will be n. In selective repeat, because we have individual acts, so some of the yellow packets can be green, like this. All right. So even though they're turned green, but that doesn't mean that they will include these 4, okay, into the window, like this. Okay, no. So what we're restricting is the maximum sequence number that can be unact, not the maximum number of packets can be unact. Okay, just to make sure that's clear. And the receiver of selective repeat is, as we talked about, more complicated. It also maintains a certain data structure, tracking the status of these packets. So we also have a window size here at the receiver. The base is now called the receive base. So receive base is always pointing at the first packet expected but not yet received. And there could be a number of these pink packets around. So these are the packets arriving okay, but out of order because there's a gap before it. So those are the out of order buffered packets. The blue ones are reasonable, okay, packets that are expected next. Okay. The black ones are just not possible. So if we receive packets after receive base plus n, we'll be just treating these as maybe hackers injected packets, spoofed packets, things like that.
Yeah, so now you know selective repeats mechanism. It sounds straightforward. But if you look at the window at the sender side and now the receiver side, selective repeat needs to buffer and track all the packets arriving out of order. So you can see complexity of maintaining the windows, both at the sender side and the receiver side. So you see that selective repeat, although more straightforward to us, to human beings, but it's actually harder to implement and make sure consistent for the coders, right? Yeah, it does. But let's check out the finite state machine of selective repeat next.
And now the selective repeats finite state machines. This is the sender side of the machine, and this is the receiver side of the machine. And you might be going, wait, they don't look like FSM at all, right? Because previously we have like states, right? And the number of transitions like these. Yeah, what I'm doing here is to do textual representation. So what I'm saying is essentially, yeah, there are still 3 transitions. So first transition is triggered by this event, the data from above. Okay. Second, the timeout event. Third, triggered by receiving an acknowledgement packet within a particular range. So later on, you will see what's nice about writing the finite state machine this way, because it looks almost like a pseudocode, isn't it? Right? So the sender side is looking like a switch procedure, where when there's the data from above event switching in, then we do this. When there's the ACK packet being received switching in, then we do that. So now let's go over the finite state machines of the senders and receivers. Sender side, when there's a call from above, okay, if the next available sequence number is within the window, yeah, send packet. And you know how to do the next available sequence number, whether it's in window check, right? So the next seq num should be less than base plus n. Second is the timeout event. If our timer times out, and that is for packet sequence number n, we retransmit packet n and restart timer. Straightforward. If we receive an acknowledgement packet, we extract the sequence number and check if it's within the send base and send base plus n subtracting 1. So that is saying, hey, whether the ACK is within the reasonable range, right? Because the send window is only this big. If we receive ACK before that or after that, that's just weird. Okay, let's just ignore those. So we'll only be handling ACKs that's within the send window. Now, once that's the case, we mark packet n being received, so turn it to green. If n smallest unACK packet, so if n here is also the smallest unACK packet, so we turn that into green. There could be a number of other greens following that. Then we could what? Advance the send base all the way to the next yellow packet. Okay, so advance the window base to the next yellow packet, which is the next unACK packet. So this is sender's actions, depending on what's triggering the sender's finite machine to take transitions. Similarly here at the receiver end, there are 1, 2, 3 transitions. First transition is if we receive a data packet that's within this range, the receive base and receive base plus n minus 1, so that is reasonable, okay, as expected. Then we send individual acknowledgement. So if it's packet n, then ACK n. If this packet is not expected, so meaning it's out of order, then we will buffer them. So these will be the pink packet, all right? Now, if this packet is actually coming in and filling one of the gray packet, so unreceived previously, but expected, then we can pass all the packets suddenly in sequence, all in pink, up to the application layer. So let's deliver those, okay, in ordered, and advance the window to the next, not yet received, but expected packet. So to the next gray packet. All right, so this is when we receive a data packet that is within the receiving window. If we get a packet, okay, that comes in, but it's actually in this range, receive base minus n to receive base minus 1. What is this? We are actually sending an ACK for that packet back. If you recall, it could happen, right? The ACK packet going back to the data center, if that packet is corrupted, the sender there is going to wait until the timer for that packet times out, then retransmit the data again. But that data has already been arrived at the receiver previously. And that's why the receiver sends an ACK back to the data at the first place. And that's before the data is found corrupted at the sender as well. Right? So in that case, we still need to send the ACK for that packet. Okay, do not ignore this. Otherwise, that timer is gonna fire it again and again and again, and the sender there is gonna retransmit the same packet again and again and again. Right? Third transition, otherwise, or the default, I'll just ignore. Okay, so receiver pretty much do nothing in case it's packet not within the receiving window or not one receiving window before. So those that are outside, just ignore it, because chances high that they're coming from hackers or previous connections, and the data somehow, the packet somehow gets stuck in the network for too long, and it's gonna be useless anyway.
All right, so yeah, you see that the finite state machines doesn't need to be always having circles and arcs. It can be written this sort of a table of pseudocodes way, right? Given now that in go backend and selective repeat, we have just one state. Yeah, 4 transitions. Of course, you can list it up as a table, all right? And as Polly mentioned, that there are not just one way to write the finite state machine of a mechanism. So if one would just write the finite state mechanism or rewrite the finite state mechanism such that there's only one state, then you essentially generated the pseudocode. Okay, so yeah, selective repeat mechanism in the finite state machine. Now, next, just like every state machine we went through, we give an example. So next is an example for selective repeat.
And let's also walk through an example of selective repeat, just like we did one for go backend. So that example in go backend is actually harder to analyze. This one, on the other hand, relatively easy. Now, it looks very much like the example in go backend. So window size 4, and we start from base 0, and the next seek number 0. Getting a call from above? Yeah, because the next seek is less than base plus 4. Therefore, we generate packet 0 and send it out. And we go on until we hit next seek equals 4. And that is not smaller than 0 plus 4 anymore, so we wait. Now, over at the receiver side, scenario similar, receiving packet 0, but the receiver's action different. Okay, for packet 0, we send individual ACK 0. Receiving packet 1, we send individual ACK 1. Well, not getting packet 2, but we'll be getting packet 3. And out of order, so we buffer and send individual ACK packet, ACK 3. So ACK 1, ACK 0, ACK 1, and ACK 3 will go back to the sender. Now, sender, upon generating packet 0, packet 1, packet 2, and packet 3 will all start the timer individually. So T0, T1, T2, and T3 will all be ticking, no worries. Okay. Now, ACK 0 now comes back to the sender. Sender receiving ACK 0 will do what? Clear packet 0. So that packet will turn green. Is it in sequence? Yes. So we advance window. Yeah. Advance window by 1 to the next unacked packet. Upon receiving packet 1, also, yeah, advance sequence by 1 because it's in sequence. And hey, so base is changed to 1 and then to 2. So that allows us to send packets more, right? So 4 is generated, 5 is generated, and they're being sent out. Well, packet 2 did not get acknowledgement, but we get what? ACK for 3. All right. So what do we do there? Yes, we actually release packet 3. So we turn that into green. But hey, packet 2 there is still yellow. All right, so this green packet 3, is not the smallest unacked packet. So we cannot advance the window size further. We cannot advance the send window further or the base further. All right, so cannot be sending more. So still wait here. Okay, so this part of go backend and selective repeat similar. Right? But now, look, packet 4 and 5 will go to the receiver. Receiver here receiving 4, out of order again, buffer, send ACK 4. Packet 5, buffer again, send ACK 5. And those will go back. Here, Timer for 4, timer for 5 will be fired because there's one timer for individual packets. Okay. So finally at this time point, yeah, timer for 2 finally expires, and therefore we resend packet 2. Packet 2 goes out, received. Finally, this is the smallest unapp packet, and all the packets subsequenting packet 2, 3, 4, 5 can be passed up, okay, in sequence to the application layer, and we send back ACK for 2. All right. So simpler.
All right, so I don't know if you guys feel the same as Polly does. Selectively repeat is actually easier to track for me. Okay. Now, last quiz this week, 22, and this one is going to be a take-home quiz. Okay, that means that you don't have to complete, okay, in class. So what I'm asking you to do is this. So we learned 2 pipeline RDT, go back in and selective repeat. Q1 asks, if the network bandwidth is limited, extremely limited, which one would you choose? Okay, go back in versus selective repeat. If the sender side memory is limited, okay, which one would you use? And if the receiver side memory is limited, which one would you use? Recall the pop-up question Polly asked, right? And many of you have expressed your opinions, and we see 2 different stands, okay? And some people argue that, hey, I would like to buffer those out-of-order packets in go back in, because otherwise it's a waste, right, of bandwidth. But some argue that if you buffer those out-of-order packets, then it will consume memory. Q4. Now, I ask you, if you are a programmer to program a pipeline RDT, which one would you choose? Okay. For your minimum effort. But you can actually argue otherwise. Which one will be more efficient? Okay. Easier, okay, for the computer to track. So Q4, let me make it a little bit open. It doesn't need to be minimum coding effort. It can be anything. But if you choose one versus another, give me why. Okay, and this is a take-home quiz. So, and you will see that, quiz 22 there is already on the Discord space. And using the last minute here, let me address a question from Yu Zheng. Okay, Yu Zheng, you're good. You're following the videos. I'm so happy to know that. Because earlier, when I'm introducing Go Backend's finite state machine, I said that, for some reason, the starting state, the base will start from sequence 1. Next sequence number is also initialized to 1. For some reason, the textbook author, when the finite state machine of Go Backend is introduced, the starting sequence number is 1, no longer 0, right? Before that, the first call from above always generate packet 0. Therefore, towards the example of Go Backend, we see that, hey, packet 0 send, and ACK 0 send. Yeah, so there seems to be an inconsistency with the starting packet sequence number. Okay, Yu Zheng, if your question is about this, so very good observation. All right. Yo Cheng would like to do the quiz as online. I know it's okay. You can work on it online, but after the lecture. But if your case is simply why ACK 0 generates packet 4, that is because when ACK 0 arrives, right, the send base gets moved to 1, and the next seek num is all moved. The gray packet is also moved to the next one. Therefore, open up one more blue packet that you can use to send the next packet, which is packet sequence number 4. Okay, So Yuzheng, hope that I answered your question. All right. Good. With that said, and this is all the time we have. Okay, let's not do too much overtime. And so this is all for today. I will see you next week. And the first exam result will be out at about 1 p.m. You guys did great. Okay, whether you have good score or not. Okay, I can tell that you did all the best you can. Okay, and some of you might be a little bit more rusty doing the PA related problem sets. Okay, but exercise more. Okay, then it will usually make it easier for you to code. Okay, under time pressure. Okay, good. So with that said, I say goodbye. I see you next week. Okay, Youcheng, it's okay. You can work on it now. Okay, bye. Hey guys, you're free to go. Yicheng, we can go back to the finite state machine here. All right. So we receive an egg, right? And it's not corrupted, isn't it? The base will be the get egg sequence number plus 1. So the base, right, is, oh, I see what you're saying. I see what you're saying. So you see that the base is advanced by 1, but you see there's constantly data coming from above. Okay, so in the example, okay, the assumption is that there's constantly packets coming from above, right? So as soon as the base is advanced by 1, there's always call coming. Immediately there's a call coming, right? And base plus n that moves the next seek num that creates one blue box, right? And therefore we can send the next packet, that is sequence number 4. Does that answer your question, Yuzheng? Okay, I hope so. Or I hope that you are not yet gone. Okay, so Yuzheng. Yeah, I hope this answers the question. Good. All right. Bye. Again. right, bye.